Hello APC Mechanics students, today we'll solve the past paper of RQ 2014, exercise number 2. Then as usual, the figure appears to be the above the text. A small block of mass m starts from rest, which means the initial kinetic energy is 0 at the top of a frictionless lamp. The moment it's frictionless, it means that we can apply the conservation of energy. Now this is the ramp, so along the ramp we can apply the conservation of energy, which is at a height h above a horizontal tabletop as shown in the side view above. The block slides down the smooth ramp and reaches point P with a speed v0. After the block reaches point P at the bottom of the ramp, it slides on the tabletop guided by a circular vertical wall with radius r as shown in the top view. The tabletop has negligible friction, and the coefficient of kinetic friction between the block and the circular wall is mu. Now, so referring to the top view, the block is being in contact with two surfaces, with the table itself and with the circular wall. As given in the text, there is no friction between the block and the table, but there is friction between the block and the circular wall, and it's given by kinetic friction with coefficient mu. Now in part A, derive, which means we need to use basically a big law, an expression for the height of the ramp h. Express your answer in terms of v0m and fundamental constants as appropriate. Now because we're interested in relating h to v0, which means we need to use the conservation of energy, and before doing so we need to take our P level, then take the P level to be the horizontal passing through the point P. So let me say, take the P level to be the horizontal through P. And now we can apply the conservation of energy. Which means in this case, energy initial is equal to energy final. Energy about being kinetic and gravitational potential energy. Now it is released from rest, and based on our choice that would be 0. The mass is given by m, then that would be mgh. H represents the initial height, and that would be half mv square 0. Now what does v0 represent? v0 represents the speed at the point P. Now we can apply the cancellation effect, then gh is given by half v0 square, and indeed h in this case, because it's a free fall, is given by v0 square divided by 2g. Now a short time after passing point P, the block is in contact with the wall and moves with the speed of v. Then basically at the point P, the initial speed is given by v0, and because there is friction between the circular wall and the block, we would expect that the speed will change. For this reason, they're telling us this is the instantaneous speed along the motion across the wall. In part B, idea 1 is the vertical component of the net force on the block, upward, downward, or 0. Now here they're asking about the vertical component of the net force. And if you think about it, because this is a table which is horizontal, so there is no vertical acceleration either down or up whenever it's moving along this circle, so which means that the net force on the block would be 0. And the justification here, it's not just to say the forces are balanced. Basically I'm talking about the pull of gravity and the normal push, and not to say that there is no motion. The important thing is to mention that there is no acceleration along the vertical. Since there is no acceleration, no vertical acceleration, then the vertical component of the net force is 0. Now moving on to idea 2. On the figure below, draw an arrow starting on the block to indicate the direction of the horizontal component of the net force on the moving block when it is at the position shown. Now here, okay, so we have justified that there is no vertical component for the net force, but however, there will be a horizontal component. And here let me justify. First of all, there is the normal push. So let me again state. Let me refer to this figure and assume this point to be point Q in which the block is here. So what are the forces acting on the block in this case? There will be the pull of gravity down. Let me say there will be the normal push Fn prime. There will be another normal push due to the circular wall toward the center. And not only these three forces, there will be the friction at the point Q, and because it's moving in this direction, friction will be pointing in the opposite direction. So let's forget about this force and this force. And these basically would be the horizontal forces. One of them is the normal push pointing toward the center, and friction will be acting downward. So these are basically the horizontal forces through the horizontal surface, but remember this is a top view, so these are not vertical or a mix between vertical and horizontal. Both of them are horizontal. Then the net component would be left down. So if you want to draw the direction of the horizontal component of the net force, it should be something like that. And now let's justify our answer. So since the normal push and here let me specify due to the circular wall, is pointing left, and the friction and also let's specify friction with the circular wall is pointing down. Then the horizontal component of the net force is pointing down left. Now express your answers to the following in terms of V0, V, M, R, mu, and fundamental constants as appropriate. What does V0 represent? V0 represents the speed at the point P. V represents the speed through the circular at any instant at a later time. Now in part C, determine an expression for the magnitude of the normal force N exerted on the block by the circular wall as function of V. And because the normal force is a centripetal force, which means we need to apply Newton's second law and we need to project along the centripetal direction. So let me say apply Newton's second law. Now it's not very important whether we say translation or rotation, but here in this case remember that this is Newton's second law for translation, although we're projecting it along the centripetal direction. So F naught would be ma. Now, what are the forces? Basically, all the forces that are acting on the block. We have the pull of gravity, we have the normal push due to the table, we have the normal push due to the circular wall, and we have the friction also due to the circular wall, that would be equal to MA. And now we're gonna, so remember, this is a vector equation. It gives the birth to several linear equations. We're gonna project along the centripetal direction. And here let me mention something very important, although it's not required in part C. But remember that friction is given by the coefficient multiplied by the normal push here, which normal push I should include Fn, which is basically equal to Fg, or N. No, basically I should include N, because both of them should be related to the same surface, okay? And this N is not related to the pull of gravity, but related to the centripetal direction. So now that would be 0 plus 0 plus, now we need to identify whether N is positive or negative, because the normal push, it is the force which is pointing toward the center, and in the centripetal motion, the center would be the positive direction, so that would be N. Friction is down, it's tangential, it's not along the centripetal, so that would be 0, which is equal to MA along the centripetal. So basically the normal push would be equal to mv square divided by the radius of the circle track, which is r. So that would be the expression of the normal push. Now in part D, they're telling us derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed v. Then again, we need to use the same vectorial equation, which is given by the pull of gravity plus the normal push plus the normal push due to the circular wall plus the friction is equal to MA. But now, because this is a vector equation, instead of projecting along the centripetal direction, we're gonna project along the direction of motion, and that would be the direction of motion, which is basically the tangential direction. Then now let's say projection along the tangential direction. And that would be 0 plus 0 plus 0. Now friction acts in a direction opposite to that of motion. If motion is up, then friction is down. For this reason, we need to have a negative sign. Then minus FF is equal to MA tangential. Now remember, friction is given by the coefficient mu multiplied by the normal push. But remember that here we have two normal push. This is related to the pull of gravity, but we're not gonna use it because these are related to each other due to the same surface. And that would be minus mu n is equal to MAT, and we're interested in determining AT. So notice that here we're interested in the magnitude and not the vector quantity as it is. So, and we're interested in expressing our answer in terms of these quantities. So A tangential, so MA tangential would be given by, or let me say the following, minus mu n is given by mv squared divided by r is equal to MA tangential, and here we can apply the cancellation effect. Then indeed the tangential acceleration in magnitude is given by mu v squared divided by r. Remember that this is the magnitude. Later on, if you want to determine something related to A tangential, we need to use it as a vector quantity. Now in part E, they're telling us to derive an expression for Vt, the speed of the block, as a function of time after passing the point P on the track. Now, so you might think about this equation, which is given by A tangential is equal to mu v squared over r. We need to determine the expression of the speed in terms of this quantity, and the way to utilize this equation is converting it into differential equation. Why? So basically we have started with this vector equation, projecting it along the vertical, which is up and down wouldn't give us anything. It would only say that the pull of gravity is equal to normal push. And because we're dealing in a three-dimensional problem, so we can project it along three different directions, no more. Okay, so already we have done, so one of them we can ignore, which is the pull of gravity is equal to the normal push. This is 1, 2, which is this one, and 3 is basically this one, and we have used n is equal to mv square over r. Then we cannot project this equation anymore in order to deal with it to find the expression for v. The second thing is that even if we know the acceleration, we cannot use kinematics in order to derive the expression of the speed, because itself the acceleration depends on the speed. So the only way to do it is using calculus and to utilize this equation as a differential equation. But remember that we need to use the negative sign and not the magnitude itself. So let me say that A tangential is given by minus mu v square divided by r. Now here we have two accelerations, AC and AT. And remember, this is due to variation in direction, and this is due to variation in speed. For this reason, AT can be written as dv by dt. Then that would be dv by dt is given by minus mu v square divided by r. And how can we solve this differential equation? By separation of variables. Then dv divided by v square is equal to minus mu over r multiplied by dt, and now we can integrate on both sides. Now the integral of 1 over v square dv, so we don't forget the dv, that would be minus 1 over v plus a constant. And if you forgot that this is given by that, you can utilize it as a power function, v to the power minus 2 dv. We add the power by 1 and divide by the final power, and that would be v to the power minus 1 over minus 1 plus c, which is basically minus 1 over v plus c. Now here I'm not gonna add the constant because I will integrate also on the right hand side. The integral of 1 is just t, because we're integrating with respect to t, plus a constant that we need to fix based on the initial conditions. Now multiplying the equation by minus sign, the constant won't be affected. That would be 1v, 1 over v is equal to mu over rt, plus this constant again. And now we can say at t is equal to 0, what does t is equal to 0 represent? This initial instant represents the motion due to friction, which is at the point P, and we know that at the point P this is given by v0. Then we would have 1 over v0 is equal to mu over r multiplied by 0 plus a constant. Then this constant basically is given by 1 over v0. Then we have fixed our initial conditions, which means that 1 over v is given by mu divided by rt plus 1 over v0. Now we need to determine v explicitly. Then 1 over v is given by, here we can do the common denominator, that would be mu v0 multiplied by t plus r divided by r v0. Then v in this case is given by r v0 divided by r plus mu v0 multiplied by t. And that's it for me in this video, guys. See you soon in a new one.